extreme values algebraically, or the first derivative test. We have discussed how critical values are found when the slope of the derivative is 0 or undefined. When the slope changes from increasing to decreasing or vice versa at a critical value, an extrema occurs. This change can be seen in the derivative as well. When a function is increasing, the derivative is positive at those x values. Likewise, it is negative when the function is decreasing. We can use this to draw conclusions about extrema algebraically using what is called the first derivative test. The first derivative test tests x values in between critical values to see whether the function is increasing, has a positive derivative, or decreasing, having a negative derivative. If the derivative changes sign at a critical value, we can conclude that an extrema occurs there. A maximum will occur at a critical value where the derivative changes from positive to 0 or undefined, if it's a corner or cusp, for example, to negative. A minimum will occur at a critical value where the derivative changes from negative to 0 or undefined, if you have a corner or cusp, for example, to positive. To help us organize the test values in between the critical values, we use what is called a sign chart. A sign chart is a number line that only lists the critical values of the function on it. Then it uses a plus sign and a minus sign to indicate whether the slope is positive or negative in between those values. Do you remember this previous example? F of x is equal to x to the third plus x squared minus 8x plus 5. We found that its derivative, f prime of x, is equal to 3x squared plus 2x minus 8, and that its critical values were x equals negative 2 and x equals 4/3. We can use these critical values to set up the sign chart with them provided. So this sign chart is for f prime of x. We draw a number line, put hashes where our critical values occur, so negative 2 and positive 4/3. Now we can pick 3 values, one within each interval. So we have 3 little intervals here. And then substitute the value that's chosen in for x in the derivative. So we want something first that's less than negative 2. Easiest thing to do would be negative 3. So if you use x equals negative 3 and you substitute it into the derivative, you will end up getting positive 13. And then now we have to pick a number between negative 2 and positive 4/3. Easiest value is probably 0. You could also pick 1. That's an easy value. If 0 is an option, I usually go to that one first because it's really simple for substitution. We can clearly see that when 0 is filled in, f prime of 0 is negative 8. So it's negative here. And then we have to select something that's bigger than 4/3. X equals 2 is probably the easiest. And if you use x equals 2, you'll get a positive 8 here. And then since f prime of negative 3 was positive 13, we put a plus sign over top of the sign chart for that interval. Because f of 0 was negative 8, we put a negative sign in between negative 2 and positive 4/3. And because f prime of negative 3 was positive 8, we put a plus sign to the right of 4/3. And that's how our sign chart is used. And now that our sign chart is completed, we can now interpret it. If f prime of x is positive, that means the function is increasing. So we can show increasing values for the 2 plus signs that were created. And where the derivative is negative, for us in between negative 2 and positive 4/3, we can draw an arrow pointing downward and to the right to show that it's decreasing. So our function's going to look something like this just from these increasing and decreasing values. And based on the conclusion that we made, we can see that at x equals negative 2, we have a maximum value. So this would be negative 2, and then if we substitute negative 2 back into our original function, we would be able to get the y-coordinate for it. And we can see that there is a minimum occurring at 4/3. So the ordered pair for that minimum value will be 4/3, comma, f of 4/3. And again, this is just a rough sketch of what's happening here. And then to determine your points of extrema, as pointed out on the last slide with the sketch there, if you substitute -2 in for f, you will get 17 out. So your local maximum will be -2, 17. And then if you substitute 4/3 in, you'll get -41/27. So therefore that local minimum value will be 4/3, -41/27. Let's review the steps for the first derivative test before we begin working through more examples. First step is to find the derivative of the function. So if you have an f of x, step number 1 is to find f prime of x. Step number 2, find the values where the derivative is equal to 0 or is undefined. These are your critical values or locations of possible extrema. So we set f prime of x equal to 0. Then we create the sign chart and test the values where f prime of x is equal to 0 or undefined. For this general, I'll just use variables a and b. And then we would substitute variables to the left of a or less than a into the f prime of x and observe the sign to see if it's positive or negative. Same between a and b. Substitute a value that falls in between into f prime of x to see if it's positive or negative. And then select a value that's greater than b into f prime of x to see if it's positive or negative. And then based on the analysis that is done with this sign chart, you can determine your local extrema, your minima and maximum values. So once we find those x values for the extrema, we can substitute those x values back into f of x. So we're finding f of a and f of b, for example, in this general form that we have here, and those will be the y values of your extrema.